Hello. So, in this lecture, I'm going to discuss a new concept called the instantaneous center of motion for an object. But before we get into that, I put another link in the YouTube playlist back to Physics 1. And in that video, I describe why rotation vectors in a plane, the rotation vectors like the angular velocity or angular acceleration, or even the angle itself, if you want to think of it as a vector, they are associated with the third direction. So I think Thomas had a question last time about why it was that rotational vectors were pointing perpendicular to the plane of rotation. Ultimately, it's really just a derivation, but it proves to be, or not a derivation, sorry, a definition, but it's a useful definition. It shouldn't be too surprising, though, given that we know that torques and things involve cross products, and which necessarily are going to involve a third dimension. So it also works out better to define angular velocity and angular acceleration as sticking out of the plane of rotation. So anyway, I attached or I included that Physics 1 video called 2D rotations into the dynamics playlist sides. That way I can really drive up my YouTube views, and really cash in on making all this money. All right. So today we're going to, let's review briefly. Last time we talked about relative velocity analysis. And that was the idea there, was that we had a basis point, which was attached to the object. And then the velocity or motion of any other point could be thought of as the velocity of the basis point plus a relative rotation term. So we're going to build on that idea and identify something called the instantaneous center of velocity. Okay, to do that, so hopefully you've read through section 16.6. And the goal for today's lecture will be to be able to locate the instantaneous center of velocity and use that to determine the velocity of any other point on a rigid body. So those are kind of the goals. And I've got a number of examples to go through with you. Okay, usual stuff. All right, reading quiz. If applicable, the method of instantaneous center can be used to determine the velocity, the acceleration, velocity and acceleration, or the force. Well, hopefully, if you've done the reading, you know the answer is velocity. And 2, the velocity of any point on a rigid body is blank to the relative position vector extending from the instantaneous center to the point. Options are always parallel, always perpendicular, C in the opposite direction, or D in the same direction. Well, if you think about it, A, C, and D all kind of are getting at parallel notions. So assuming that there is an answer, the odd one out is going to be the right one, and which is correct. B is right. The velocity vector of any point is perpendicular to the relative vector extending from C to that point. Always perpendicular. Okay. So here's a picture. If you look at that wheel, so kind of use my arrow to kind of go around. Here you have a bicycle tires going around like this. Oh, excuse me. And at any point on that tire, oh dear. So take a point here. This point is, so the tire is rotating, but it's also traveling forward. So it's, so typical point would have a mixture of rotation and translation. And what we notice is at each point, if you kind of plotted the total velocity of that point, then what you're going to see is that the velocity vectors are all perpendicular to, they call them lines of action in the notes, which extend back to the contact point where the tire actually touches the ground. And this is a point where instantaneously, at that moment when it's in contact with the ground, the velocity of this point is actually 0 because it's rolling without slipping. So the velocity here is 0, and the velocities of any other point are perpendicular to the lines of action back to that point with 0 velocity. And so if you think about it, that means if you were standing right here at the point where it touches the ground, it would look like the entire wheel was rotating about you. So it's as if every point on the tire is undergoing a pure rotation about this instantaneous center of velocity. So that's kind of an interesting thing to think about. There'll be some more pictures here. So I think the tire one's actually not the easiest one. I'm not sure why they started with that in the slides. I think there are other ones that are easier to mentally picture. The other thing to think about is what point on the tire has the biggest velocity and which one has the smallest velocity. Well, we know that the one with the smallest velocity, or I guess speed, is here at the contact point. What point on the tire actually is moving the fastest? Well, if this has velocity 0 and the center of the tire has a velocity v, and it all has to kind of move together, you kind of know that at the top, the velocity has to be twice as big as the center so that they kind of average out to give you overall motion with this velocity v. And that actually turns out to be true. The point at the top of this tire has the fastest velocity, and the point at the bottom of the tire has 0 velocity. So you can think about the last question too. Does a larger wheel mean the bike will go faster for the same rider effort in pedaling than a smaller wheel? Think about that. Okay, I think I like this picture better than the last one. So here's a picture where you have a board, it could be like a meter stick or something. And you basically, you can focus on 2 points. And I think that's why it's easier than the bicycle tire. This point will slide along the ground, and this point will slide along the wall. And if you think about it, if you kind of imagine floating out here, and maybe you're riding on the top of a bumblebee or something, and you were to look at it, in that instant, depicted in this snapshot, it would look as if this board is in a pure rotation about you. Okay, so if you were standing up here, the board would look like it was undergoing a pure rotation about this point here. That's the idea of an instantaneous center. It's the point about which the rigid object looks like it's undergoing a pure rotation. All right. Oh, just a comment here. So one thing is, how can this help you? Well, if it's a pure rotation, then we have a really simple form for the velocity. Here, let me go back here and write it down. So if you have a pure rotation, then you would say that the velocity of any point, A, would be, well, we'd want to say, you could write it as a velocity about point C plus omega AC cross R A relative to C, except if at this point C, it's a pure rotation, this is 0. So we see that whenever you have a pure rotation, the velocity formula simplifies, and I'll rewrite it here. And just to be that the velocity vector is an angular velocity cross a relative vector. Okay, so that's really the beauty of it, that it becomes the velocity of a point has a kind of a simpler form because you can remove one of the terms. And furthermore, because the object is rigid, all points would have the same omega. I suppose if you had a rubber sheet, this concept probably wouldn't be much use. It'd be because you'd have a different, if the board could flex, then you could get different omegas at different points along the board. But as long as it's a rigid board, then this is a useful concept. What about the direction of or the center of velocity of the velocity of the center of gravity? Or maybe we just plot the position of the center of gravity. And what I want you to do is imagine the board started out vertical, and then it started to slide down. And I'll change colors here. If you were to plot, oh dear. If you were to plot the center of gravity, it would start out kind of lying along the wall, and then it has to end up lying along the ground, and it would follow something like this kind of a pattern. So the center of motion, which is up here, is not the center of gravity. They don't move in the same way. Okay, so that's kind of an interesting observation. Okay, let's go back to the slideshow. All right, so why would this be a useful idea? Because it simplifies the velocity formula, and it gives us one number, omega, which characterizes the motion of every particle. I say one number, really it's one vector, but in planar rotations, it's one number, which characterizes the motion of every point on the rigid object. Okay, so that's why we're doing this. So for any body undergoing planar motion, there always exists a point in the plane of motion at which the velocity is instantaneously 0 if it is rigidly connected to the body. This point is called the instantaneous center of 0 velocity. And they emphasize in bold, it may or may not lie on the body. And typically it doesn't. The example we saw in the last slide showed that. And then there are ways to figure it out. So what's this definition is pretty complicated. Um, so what's going on here? Let me escape, and I will go. I think I'll just do a new slide. Well, that didn't work. Insert new slide. Just want a blank slide. Sure, we'll just do that one. Okay, so here's the idea of this. So you imagine you have some sort of an object, and there are 2 points on it. Call them A and B. Okay, and they're moving in some crazy way. You know, I don't know. I'll change colors here. We'll say they have velocity vectors this way, and let's say this guy's going that way. Okay, so you have 2 points, and they're undergoing, you know, more or less, well, arbitrary motion. So their absolute velocities vectors are just arbitrary. But the idea is to mentally kind of enlarge this object if you want. And so you can kind of imagine that the original object is embedded in a larger object. And so the original object is embedded in this larger object and rigidly, so that the larger object moves with the original object. So the green object moves with the black object. And the point is then there's some point, some location in this larger object about which everything is just rotating, and it undergoes a pure rotation. And because we know pure rotations have velocity vectors which are perpendicular to the relative vectors, we can figure out various things. So we know, for example, that if everything is kind of rotating with some large omega, some angular velocity, about some point, we can kind of reverse and figure where that must be, because the velocity of every point in a rigid object that is undergoing pure rotation is perpendicular to the relative vectors. And so for 2 objects here, for example, the place where the relative kind of lines of action cross, that must be, and your book calls this the IC for Instantaneous Center. I think other books just call it C for center. Anyway, that's the instantaneous center of rotation. Your book does not prove that this is always possible. And I worked out a proof. It's a little complicated, so I think I may add that in another video if I kind of work up the energy to do that. It's a little tricky. Basically, what I did was kind of write down velocity vectors for for 2 arbitrary points, and just kind of showed that you could write it as a pure rotation about some third point called, you know, IC in the textbook. And then I had to, the tricky bit was to show that the actual location of this third point is independent of which 2 points you choose, A or B. They could be anywhere in the object. So it was kind of a little bit, at least the way I did it, it wasn't just an obvious one-line thing. It was, you had to kind of think about it a little bit, or I had to think about it a little bit. So probably shows I'm out of practice with trigonometry and vector identities. Okay, so that's kind of the idea. So mentally, what you could do is identify a new point, which may or may not be in the body. And about this new point, the original object is undergoing a pure rotation. Remember, if something has a pure rotation, then the fixed point of that rotation, this new point, the instantaneous center, will have no velocity. So I'll write that here. That's actually the really important thing. So that we will use several times here. The velocity of the instantaneous center is going to be 0. It's the pivot point of the rotation. Okay, think of it, it's the point that actually doesn't move. Think everything else rotates about it. That's the important thing to remember. Okay, so let's go back to the slides. And okay. All right, so they're going to talk about how to find it. There are a couple ways we can do it. There are basically 3 cases. Just a new Jeopardy word right here. Jeopardy is this word centrode. So the instantaneous center is only a point about which things are rotating at one instant in time. And at different moments in time, there would be a different instantaneous center of the motion. And if you kind of traced out their paths, that gives you a curve called the centrode. I'm not sure. I don't think I even saw that quite defined in your textbook. It must have been there. But I didn't see it. So that the centrode is what if you kind of sweep out all of the family of instantaneous centers, that's the curve that you would get. All right. So how could you locate it? Well, the first way you can locate it is actually I don't know if it's it maybe. Anyways, imagine you knew. Okay, so let me go back here. So let's sorry, struggling with. All right, so if you know that the velocity about the instantaneous center is 0, you can say the velocity of any point A is 0, the velocity of the center, plus omega, the angular velocity of the object, times the relative vector, the cross product between the relative vector extending from the instantaneous center to A. So notice then, if you're trying to find the instantaneous center, case number 1, they say, is if you know the velocity and you know omega, you can figure out the radius. And if you work this out in magnitude form, this would say that the magnitude of the velocity equals the magnitude of the scalar angular velocity times the relative magnitude of the relative vector. So that gives you the magnitude of it, and then you know that it has to be perpendicular to the velocity vector, and so you can work backwards to get the position of the instantaneous center. All right. Oh, they make a nice observation. Notice in this case, the particle is the point A is kind of arcing, if that's even a word. It arcs like that, and the instantaneous center lies kind of at this, if you think of it as like being part of a circle almost, it lies up here towards the center of that circle. So so because this thing is rotating like this in a clockwise fashion, the center is going to be up and to the right of that point. If it had been curving downwards, then the center would have been down and to the left. So just it's kind of useful just to have a feel for where these things could be. All right. Another way of finding it, and this is actually the way I suggested in my hand-drawn picture. If you know the velocities at 2 points, you can, or actually, if you know the directions of the velocities, you don't actually have to know the velocities. You just have to know the directions of the velocities. Then you can draw lines which are perpendicular to each of them, and where the lines crisscross, then that's going to be the center, right? So that's a personally, that's usually an easy one for me to use. I use that one a lot. Okay. There we go. Okay, and then there's a third way to use this, and so, well, all right. So what this is really using is the fact that the object is rigid, or sorry, that you could imagine your object is embedded in this larger kind of object, which is rigidly rotating about the center of motion. And that means that every point has the same angular velocity about that center. So if you know that, then we can say, kind of going back to physics 1 language, you know that the velocity of each point is omega times the radius of that point, and they all have the same omega. So at any 2 points A and B. And if you turn it around and think of this as VA over VB, or sorry, RB, sorry, VA over RA, that has to equal VB over RB. This was a radius, which means that you can think about similar triangles. So you could, like in this example here, they've got a triangle, and the opposite side is going to be the velocities, and the adjacent side is going to be the radius. And because they're similar triangles, this angle and this angle must be the same. And they are, the vertex is the center of the instantaneous center. So this can be used in several ways. One is you can use it to figure out where the center is, or maybe even more useful, if you know you have this relationship between these 4 quantities, if you know 3 of the 4, you can work out the fourth. So that's a useful way to do it. And it doesn't matter actually whether whether you're kind of the center is in the middle of the object or outside, you get the same similarity because it really comes back to this ratio. So that's the idea, or that's the third case where you can use this productively. This is really saying the exact same thing that I did, that that about the instantaneous center, the object looks like it's undergoing a pure rotation, so that for any point in the object, its velocity is r omega when you write it out with scalar quantities. Okay, and they have an example here. So if you want, the darker blue, the darker light blue is the original object. The lighter light blue is kind of shows you where the extended object is, and then the instantaneous center is there. So that's all right. let's go on to our first example. So this is an example where we can use these techniques to understand the angular velocity of links AB and BD. Okay, so I'm going to do this on the, I'm going to insert a new slide and work through the example there. All right, so let's go back one just so you can see. So we have a surface, and we have a block which slides along the surface, and we have a pivot point here at A, and this block has a known velocity, and you can see what's going to happen as the block moves to the right. It's the this hinge is going to flatten out. Okay, the two lengths of the rods are the same, and okay, what they want us to do is to find the angular velocity of both links, both rods. So the first thing we should do is kind of think about how points are moving in this picture. So I'm going to draw the motions on, superimpose them. Point D is clearly moving to the right, so I won't draw that one there. Okay. A is fixed, it can't move at all. B, well, because this is a rigid link, point B has to move along a circular arc perpendicular to the link. So B must be moving that way, sorry. It has to move straight down, or not down, sorry, has to move diagonally. And because this is a 45-45 right triangle, B actually moves along the body, or its velocity is actually along the instantaneous link, the direction of the link at this instant, link BD at this instant in time. And then they give us the various quantities, the lengths and things, angles. So point B is instantaneously going kind of down and to the right. Point D is moving to the right. And so we want to try to figure out where the instantaneous center of the velocity could be. So take a second here before I tell you the answer. Think about which of the cases, there were 3 cases I went through where you could figure out the instantaneous center. The first case was when you knew omega and you knew a velocity of 1 point. Well, I don't know any omegas in this one, so that's not going to help us. The second case was when we knew the velocities of 2 points on a rigid object. That's exactly what we have here. Well, we don't know the velocity, but we only need to know the direction of the velocity. And that's exactly what we have here. We have the direction of the velocity at point B, and we have the direction of the velocity at point D. And what we should do is draw the lines of action which are perpendicular to the velocities. So I'm going to change colors here. So the lines of action I'm going to put put those in red. So the line of action here is going to be this way, and I'll do this one in green. The line of action for this one, for point D, is straight up. And where those cross must be the instantaneous center, which has, and where the velocity around the instantaneous center is 0. So we're talking about the velocity. Well, okay. So that's the instantaneous center for link BD. Think for a second, where is the instantaneous center for link AB? Where's the place that has no velocity associated with link that we want to associate with link AB? Hopefully you figured it out. For link AB, the instantaneous center of motion is going to be here at A. Let me choose a better color, something more visible. Do it in yellow. The instantaneous center for link AB. Okay, this is for link BD. Okay, so we know that the first instantaneous center is here, or sorry, it is up here, and the second one is here where A rotates at point A. All right, so we've identified the two, conceptually where the instantaneous centers of motion are. We have to do some trigonometry to get numbers, but okay. All right, so take a second and why don't you pause the video and try to figure this out. First, I would find the position, do the geometry to figure out where this point actually is. And then once you have that, you can use it. You can basically go from the velocity at point D to finding the angular velocity about this point, or the instantaneous center. And once you have that, you can figure out the velocity of B. And once you have the velocity of B, you can find the angular velocity of link AB. So that's the way you should proceed through this problem. So take a second, work that out, maybe pause the video. All right, so here's my solution. Okay, so I have point A, I have point B, and I have point C. And I know these lengths. Oh, yeah, sorry. These are all 0.4 meters. And this is 45 degrees. And so is this. Now, we said that we needed to extend this up here to find the center. But because this is 45 degrees and this is all part of a right triangle, I know that this is 45 degrees. And basically that tells me that this side, this length must also be 0.4. And this length must be, well, that's a 45, 45 right triangle. This must be 0.4 times the square root of 2. It's this length of side. And working that out, that gives me 0.566 meters. Just doing the trigonometry. All right. Now, this point up here is the instantaneous center for link B. I got it, not C, it should be D. I apologize. For BD. So that means, let's kind of write this out. That means that, well, I know that the velocity of D should equal omega BD cross the relative vector of D relative to the instantaneous center. And if I take magnitudes of everything, remember the angular velocity points in the z direction, so it is perpendicular to the radius here. So there's no sine of theta in the magnitude formula. It's just going to be omega times r. That's going to be, looking at the problem, the velocity of d was 3 meters per second. So this is going to be 3 meters per second equals omega BD times the relative vector from the instantaneous center of BD up to D. That's going to be 0.566 meters. And therefore, omega BD must equal 3 divided by 0.566, and plugging in numbers, I get 5.3 radians per second. Now, okay, so that's just what I get. And you can kind of see this is a little bit bigger than a half, which means 3 divided by it should be a little bit less than 6. So seems about right. Okay, now the point is here that the entire link BD undergoes a pure rotation about this point, which means that the angular velocity of point D was 5.3, but that's also the angular velocity of point B about the instantaneous center. So I know that I can write, I basically use the same formula, but now apply it to point B. So I'm going to insert a new slide. Try to do that. So the instantaneous velocity of point B, well, that should be this vector. We're not going to worry about the vector quantities because the geometry is so simple, we can just write the vectors down by sight because it's all, it's on 45-degree lines. So we want to work out the magnitude of this. And what we find is that the velocity, or sorry, I guess the speed of B, the magnitude of B's velocity, is going to be the same 5.3 number times the length of the relative vector from B to the instantaneous center. Well, if I go back, I see that that vector was 0.4. So it's this times 0.4 meters. Multiplying that out, and I get 21.2 meters per second. Okay, so now I have the velocity of B, but on the other hand, we know that the velocity of B has to be along this 45-degree line, which kind of is down and to the right. So I can immediately write down the vector form of the velocity of B is 21.2 meters per second times the unit vector, which is along a 45-degree line down and to the right. That's going to be x hat minus y hat over the square root of 2. If that's, just take a second. If that wasn't obvious, just take a second and work it out. But you know it's along that, has to be at a 45 line with slope -1, has to be along that link. So parallel to the velocity at B. All right. Okay, so now we know the velocity of b in vector form if we wanted it. The last thing we have to do for the problem is to find the angular velocity for link A, B. And to do that, I know that A is the instantaneous center for link AB, which means that about point A, you can just think of B as undergoing a pure rotation. So I know that it must be that the magnitude of the velocity of B equals omega AB times the the size of the relative vector, which would be RAB. Sorry, apologize. Mixing notations here from different classes. B relative to A. And looking back at our previous slides, you can see that this number is 21.2, and this is what I'm trying to find. And this vector has length 0.4. These are all magnitudes of vectors. And dividing it out, you get that omega AB equals, I guess shouldn't be any real surprise, at least the magnitude of it must be 5.3 radians per second. Now, you could have said, well, duh, it's a 45-degree angle, and that basically means that up to minus signs having to do with clockwise and counterclockwise, that any number you get from the right side of the triangle has to be the same as the number you get on the left-hand side of the triangle. And I would say, you're not wrong. That was right. So by symmetry, we probably, if we had really thought of it, we probably could have argued by symmetry that it had to be that way. One thing I wanted to point out, this rod is going to rotate counterclockwise. So omega BD should be positive, whereas as this point B kind of migrates down, you can see that this angle is squeezing towards zero in a clockwise fashion. So actually, if we're being careful with minus signs and things, the actual minus sign, keeping with the standard math definition, would be that omega AB equals minus 5.3 radians per second. Okay. There you go. So that is an example using instantaneous centers of motion twice, and kind of tying the pieces together to analyze a link system. We can check here. You'll notice, as is pretty typical, I'm finding in these, they are pretty sloppy about clockwise and counterclockwise, or it's in the diagram sometimes, but sometimes it's not right in the diagram, and you just have to be careful. So because I don't want to worry about minus signs, I usually try to anchor my conventions to the standard math definitions, but just think through it carefully. Here's another example where we have a gear system. So there's a gear here, which spins. It's being pulled forward with a velocity of 6 meters per second. B is not, it's a gear rack, it's fixed, it's not moving. Because of the gear teeth, we know that at this point there can't be any slipping. Okay, so this is going to roll without slipping, not about the bottom of the large circle, but instead about this point of connection. Okay. So the goal is to find the velocity of point A on the outer gear. So what are we expecting? Well, you're kind of expecting, if you think back to the bicycle example, we're expecting a point at A to be moving forward and also upward. So we're expecting something kind of on a diagonal. So it's always good to sort of have a picture of what you're hoping to get after you do all this work, because there are a lot of minus signs, as I'm sure you are starting to notice. So I'm kind of expecting something like this for the velocity. And let's take note of what information we have. We have knowledge about the outer radius. We have knowledge about the radius of the smaller set of gears. And we also have knowledge of the velocity. Okay, so take a second and try to solve that problem. Okay, so hopefully you've had time to think about how to solve this problem. I'm going to insert a slide and show you my solution, and then we'll see how they do it. There's no one way to do any of these things. So if you like their way better, that's fine too. All right. So in this problem, so I have a small wheel and I have a large wheel, and then I have the fixed surface down here. So, and I know that this point does not slip. Let's call that, well, I'll give that a name in a minute. So, furthermore, I am looking for the velocity at point A, and I know at the center, point O, the velocity at point O is 6 meters per second x hat. Right. Okay. So what I notice is that this point is not moving, has zero velocity in that instant, which means that this is the instantaneous center. The point of contact is the instantaneous center for this rigid object, this set of gears. That means that I can say two things. I can say, first of all, that the velocity at point O equals a pure rotation about this point. Okay. And I can say, because the point of the instantaneous center is that every point in the object is rotating about it with the same angular velocities. So I can say the velocity at A is also written as omega cross, and now this should be the relative vector from the center of motion to A. Right? So the nice feature here is that all objects are rotating with the same omega vector. All right, I'm going to solve this problem using vector notation, because the last one I used scalar notation, just to show you can do it either way. So using vector notation, or vector analysis, I'm going to say that, so here's my strategy. I'm going to use VO to find omega, and then I'm going to use omega to find VA. All right, so that's my plan. for how to attack this. So let's work out VO. So VO is going to be, so if I write VO equals omega, so I'm going to write that as omega, scalar omega times z hat cross the relative vector from the center to the origin. Well, that just lies along the y-axis. And if you look back, that's just going to be 0.3, the small radius, or the smaller radius, times y hat, because it's going to go from the center up to the origin. All right, so when I do that cross product, I'm just going to plug in the things that I know here. I've got 6 meters per second times x hat equals omega z cross y. So let's think about that. Z cross y is negative x hat. So that's going to be omega times 0.3 times negative x hat. And I learned that omega equals negative, let's see here, this would be 220. Does that make sense that it's negative? Well, think about it. You're pulling it forward. This is going to rotate clockwise. Does that make sense? So good so far. So now we have omega, and then if I want to, I could write omega vector as minus 20 radians per second z hat. All right, so I'm going to use that form here, the vector form, not the scalar form. Okay, so now I'm going to make a new slide. Oh, son of a gun. Okay, draw again. So I know omega. Oh, so now I can use that same omega to find the velocity at point A. So the velocity at point A as a vector equation equals omega, and it's the same omega, cross the relative vector from the instantaneous center to A. Right? This vector, if you look at the diagram, I'll go back and look, because these are on, because point A is just kind of horizontally across from the center of the wheel, I know that this vector has to be proportional to the x hat direction. So if I go back and write that out, I can write this out. So I can write this as, putting in my numbers, this is going to be 0.6 x hat. And if it goes from the center, oh, I'm sorry. Take that back. That gives you the position of A relative to the center. So let's work it out relative to the bottom of the wheel. Let me go back and do that again. So the outer radius, so here's a point of contact, and this is the point I want. And the problem tells me that this distance is 0.6 and that this distance is 0.3. So I get that the vector RA I see. So the position A relative to the instantaneous center is going to be, well, think about it. If you're standing here to get to A, you will need to go back and up. So it's going to be negative 0.6 x hat plus 0.3 y hat. All right, sorry about that. And now I can just work out the cross product. So I say the velocity of A is going to be minus 20 z hat cross minus 0.6 x hat plus 0.3 y hat. And just working those out, I'm going to get 20 times 0.6, and then I have z hat cross x hat, that's going to be y hat, and then I have plus, and I'll have minus 20 times 3, z hat cross y hat, which is x hat, it's negative x hat. Sorry, there's a minus sign there. Minus signs are killer here. Okay. That's why it's useful you should have a good mental picture of what the answer should be so that we can check that this thing even has a chance to be right. Okay, so then I multiply all those out and I get, let's see here, I get 6 meters per second in the x direction plus 12 meters per second in the y direction. Or writing out with the magnitude and direction, I get the magnitude of the velocity of A is 13.42 meters per second, and the angle is 63.4 degrees. I just want to say, though, think back to the beginning. When I said what I thought the answer would be, I thought the answer would point up and to the right. So it should be, I would expect the components of my velocity vector to be plus plus for the x and y components. So it's good that I get plus and plus. So it's got a chance. Let's see how we fared. All right, well, that's what we had. That's what we had, and that's what we had. It's amazing. It's a miracle. I'm not going to lie. The minus signs can be tricky. And when you read in the book, they're pretty quick with them. And personally, I find the minus signs to be the hardest thing in the whole analysis, really. It's just, but it is just a matter of being careful, thinking it through, and solving lots of problems. All right. Okay, so here's our concept quiz. We're gonna start class with this next time. So take a look. When the velocities of 2 points on a body are equal in magnitude and parallel but opposite in directions, the instantaneous center is located at, think about that. And then finally, the next one, when the direction of the velocities of 2 points on a body are perpendicular to each other, where is the instantaneous center located? So think about those, maybe draw little triangles, you can figure it out. And we will start class with those on Tuesday. And then we'll work through a group problem And I have a few other examples that I worked out. Maybe I will go through. These problems, they take some time to kind of work through all the little details. So make sure to look at the problems. All right. See ya.